Hello everyone, welcome back to my channel. In this video I will teach you how to design a dog-legged staircase. Let us start with a problem. Design a dog-legged stair for an office building in a room measuring 2.8 by 5.8 meter. Clear vertical distance between the floors is 3.6 meter. The width of flight is to be 1.25 meter. Assume imposed load of 3 kN per meter square. Use M20 concrete and Fe415 grade steel. Assume that the stairs are supported on 230 mm width support at the outer edges of the landing slabs. Sketch the reinforcement detail. So that is the question that is given to you. Let us start designing it. For designing, we first have to mention the data that is given in the question. Let us start writing the data that is given one by one. Here the dimension of the office building or the stair wall we can say is given as 2.8 by 5.8 meter. Then the clear distance between floor to floor, that means the vertical distance between the floor to floor is also given, which is of 3.6 meter. Then the flight width is given, which is nothing but your width of the stair, which is given as 1.25 meter. And then the imposed load which is carried by the stair is also given to you. That is nothing but the live load which is acting on the stair is given, which is of 3 kN per meter square. And the grade of the concrete as well as the steel is given. The concrete grade is of M20, that means FCK is 20 Newton per mm square. And the steel grade is of 415, that means Fy is 415 Newton per mm square. Here the staircase is supported on the walls at the supports at the outer edges, and the thickness of that support is given, which is of 230 mm. So this is the data that is given. Now let us start designing it. To design the dog-legged staircase, the first step is to find the dimension of the stairs. So to find the dimensions, before we find the dimension, we have to find how many number of flights we are going to provide. So to find the height of one flight, the formula is, it is the total vertical distance, if half of the total vertical distance. If we divide the total vertical distance between any floor with 2, we will get the height of the one flight. So the total vertical distance is of 3.6 meter. So on dividing 3.6 with 2, we get 1.8 meter. So this is the height of one flight. Now let us find the number of risers and threads which has to be provided. To find the number of rise, we had to multiply the height of the flight, we had to divide the height of the flight with the rise height. Here the data of height of the rise as well as the width of the thread is not given in the question. If it is not given, then you had to assume it in between the range 150 to 180 for rise height and 230 to 300 for the width of the thread. Let us assume for our problem as the height of the rise as 150 and width of the thread as 300 mm. Now to find the number of risers, we need to divide the height of one flight with the height of the rise. Here the height of the rise is 150 and the height of the flight is of 1.8 meter. Let us convert that in terms of mm by multiplying it with 1000. Now on simplifying these two, we get a value of 12 numbers. So this represents the number of risers that has to be provided in the staircase. Now let us find the number of threads. So the number of threads to find is the formula. We have the formula number of rise minus of 1. Thread will be always 1 less than the number of rise. Here we got the number of rise as 12 and that minus 1 gives you 11 numbers. So that completes the step, that is number of threads. Let us move to the width of the landing. Here we have to find the width of the landing if it is not given in the question. We will be keeping the width of the landing that is equal to the width of the stair. In the question, the width of the flight is given, which is nothing but your width of the stair. We will be giving the width of the landing as same as the width of the stair, that is 1.25 meter. Let us keep the same value here, 1.25 meter. Then let us find the going. Going means the slope of the length of the sloping side of the stair. And to find that, we have the formula number of threads multiplied by its width. So we have assumed the width of the thread as 300 mm and we got the number of threads as 11. Let us multiply it. We get 3300 mm as our going width. So that gives you the step number 1. Moving to the step number 2, to find the effective span. So for finding the effective span, we have the formula effective span is equal to clear span plus bearing or support width which is provided at the outer edges of the stair. Here the clear span, what you have to take is the dimension of the stair hall is given as 2.8 by 5.5. We always have to consider the larger dimension here. The larger is 5.8 meter. So let us keep that in terms of mm, that gives you 5800 mm plus the support width that is provided on the either side. So that is given in the question. The width of the support is 230 mm. So let us add both the values. On adding, you get a value of 6030 mm. That gives you the effective span of the stair. So that completes the step number 2. Moving to the step number 3. In step number 3, we had to find the effective depth of the waste slab. So to find that, we have the formula effective depth is equal to effective span divided by 25. We are adopting the ratio of effective span to effective depth as 25 here. Now we got the effective span length as 6030. Let us keep the value here. That divide that with 25. So we will get a effective depth of 241.2, approximately consider it as 250 mm. So this is the value of effective depth of the waste slab. Now from the effective depth, let us find the overall depth. To find the overall depth, that is capital D, which is given by effective depth plus the effective cover. For staircase, let us assume a effective cover of 30 mm. So this value will be not given in the question. If it is not given, then let us assume it as 30 mm. Then add both the values. On adding, you get a value of 280 mm as your overall depth. Once all the length and the depth is found, let us draw the staircase, plan of the staircase here. So to drawing the plan, see the plan of staircase consists of two parts. One is the going part, other is the landing part. So the gap which you can see, which is left out before the going, is the opening that is provided in between the support as well as the stair. Here we have found the width of the going, that is 3300 mm, and we kept the width of the landing as same as the width of the stair, which is of 1250. We don't know what is the value which is coming in between the support as well as the staircase. To find this, we know the total clear span length, that is of 5800 mm. Let us subtract the total length with addition of these two. On subtracting 5800 mm with the addition of these two values, the value which is left out is 1250. So let us do the calculation here. So the total width is of 5800 minus of, add 3300 with 1250. So you get 1250 in the beginning also. So once all the values are known to you, you keep those values within the figure. So that gives you the plan of the staircase, just for your reference. So that completes step number 3. Let us move to the next step. In step number 4, we will be doing the load calculation here. See, the load will be divided into two parts. The first part is the going part, that is the sloping side of the staircase, and the second part is on the landing side. So now the load calculation will be done differently. First for the sloping side, other for the landing side. So now let us consider the load calculation only for the sloping side of the slab, that is sloping side of the staircase. So to find that, we first have to find the self weight of the slab here, which is acting on the slope. Here the self weight of the slab which is acting on the slope is given by overall depth multiplied by density of RCC. We got the overall depth as 280 mm. If we convert 280 mm in terms of meter, we get 0.28. 280 divided by 1000, that gives you 0.28. So that multiplied by 25. On multiplying these two, we get a value of 7 kN per meter square. Then let us assume a floor finish for the slab as 0.3. We can assume a value in between 0.3 to 0.5 kN per meter square. Here I am assuming a 0.3 value of floor finish for my calculation. Then you add these two values. On adding these two values, you will get the total self weight of the slab. So that is of 7.3 kN per meter square. Now let us find, that is let us find the load on the sloping slab. Again, this will be divided into four parts. One is the load which is acting on the horizontal span, other the load which is acting on the step itself, other the live load which is acting on the overall stair, and then the finish, floor finish, or we can say it as top finish. So let us start with the first load calculation, that is of load on horizontal span, which is given by the formula Ws into square root of r square plus t square divided by t, where the value of Ws, just now we found the value of Ws as 7.3. Let us keep the value here. Root under r represents the height of the rise and t represents the width of the thread. We have assumed a value of 150 mm as rise height and 300 mm as thread height in the very first step itself. Let us keep those two values in terms of meters. Then divide that with 0.3. Now let us start simplifying this. During the simplification, you first have to add the squares of the values. Then you put square root for it. Then you divide that with 0.3. Then you multiply that with 7.3. So we will get a value of 6.1616. So let us round it off to 8.1616. Let us round it off to 8.162 kilonewton per meter square. So that gives you the load which is acting on the horizontal span of the slab. So then moving to the dead load which is acting on the step, that is found by the formula r divided by 2 into density of RCC, where r represents the height of the rise and which is of 150 mm. If you convert that in terms of meter, you get 0.15 divided by 2 into 25. Let us try to simplify this. While simplifying, you need to multiply 0.15 with 25, then divide that with 2. You will get 1.875 kilonewton per meter square. Similarly, let us write down the imposed load which is acting on the stair, and that is given in the question as 3 kilonewton per meter square. Whatever the value that is given, whether it is given in terms of imposed load or if they give the live load, for both the cases, the value has to be kept for the calculation of both the sloping slab as well as the landing slab. Then let us assume a top finish of 0.3, same as here, kilonewton per meter square. Then finally you find out the total load by adding these four values. Let us add 8.162 with 1.875 with 3 and then with 0.3. On adding these four values, we get a total load value of 13.337 kilonewton per meter square. If we want to find the load per meter, then you multiply your value with 1, because 1 represents the width of the stair, and we will be assuming the width of the stair is of width of the staircase is of 1 meter here. So for which per meter length we are finding the length of the stair is of 1 meter. On multiplying 13.337 with 1, we get a value of 13.337 kilonewton per meter. So that gives you the total load. Similarly, let us find the factored load. To find the factored load, you need to multiply your working load with the factor of safety 1.5. The working load is of 13.337. Multiply that with 1.5, you get a value of 20 kilonewton per meter. So this value gives you the value of the factored load which is acting on the sloping side of the slab. So that completes the first part of the calculation. Let us move to the second part. On the second part of the calculation has to be done on the landing slab. So let us find it one by one. Here the types of the load which is acting is self-weight of the landing slab itself and the live load which is acting over the slab and then the floor finish. So now the self-weight of the landing slab is found by multiplying the overall depth with the density of RCC. Here we got the overall depth value as 0.28 into 25. Multiplying, you get a value of 7 kilonewton per meter square. And the top finish, let us assume it as same, that is 0.3 kilonewton per meter square. Imposed load which is acting on the landing slab is also same, that is given in the question, and which is of 3 kilonewton per meter square. Now let us add these three values. On adding these three values, we will get a total load which is acting on the landing slab of 10.3 kilonewton per meter. Then here on adding this, the value has to be multiplied with 1. If you multiply that with 1, the load you will get will be total load per meter. Hence, I have directly written this as 10.3 kilonewton per meter. Then you convert this working load in terms of factored load by multiplying the value with 1.5, that is of factor of safety. On multiplying 10.3 with 1.5, you get 15.45 kilonewton per meter. So that completes step number 4. Let us move to the step number 5. Here we will be finding the bending moment which is acting on the slab. For finding the bending moment acting on the slab, we need to draw the load distribution figure. So the load will be distributed in this manner. So here the middle portion represents the going portion, and the second portion represents, the last portion represents the landing portion, and the first portion represents the gap in between the staircase and the slab. Here for the going, we have to consider a value which is from the loads on the sloping side, because the sloping slab itself represents the going. So this is your sloping slab. From here to here you are having sloping slab, and then you will be having the horizontal slab. So now we had to find, we got the load of the sloping slab as 20 kilonewton per meter. Let us keep it as larger UDL. Let us name it as WU1, which is of 20 kilonewton per meter. Then the last part represents the landing part. So the landing part, we had to consider the factored load which is coming from the landing slab. So the factored load what we got is 15.45 kilonewton per meter. Let us keep it as smaller UDL acting on both the first phase as well as the last phase of the slab, which is represented as WU2, and the value is 15.45 kilonewton per meter. Then you just have to split the slabs, span of the slabs here. We got the going width as 3.3, that is 3300 mm we got in the very first step itself. On converting that in terms of meter, we get 3.3 meter. And then the width of the landing is from the center of the support. We got the width of the landing as equal to width of the stair, which is of 1.25 meter. But here I have written 1.365. That 1.365 I got from width of landing plus half of the support width. So on adding the half of the support width, you can get a value of 1.365. Whatever the support that I have shown within the figure, that is from the center of the support. From the center, the width of the landing is 1.365. Similarly, you get the width of the clear distance from the center of the support as 1.365. Then the overall effective length of the slab is written as 3.06 meter. So this is the figure for considered for the calculation of the bending moment. In the next figure, what I am doing here, I am just converting the UDL in terms of point load so that the calculation part will be easy. Now, let us convert the first part of the UDL in terms of point load. To convert that, you have to multiply your UDL with the distance. Let us multiply 15.45 with 1.365. On multiplying 15.45 with 1.365, you get 21.09 kilonewton per meter, and that point load will be acting exactly at the center of the span of 1.365. Center of the span means the distance of now the point load with respect to the edge will be 0.6825 meters. Similarly, let us convert this UDL part in terms of point load, but we know that the maximum bending moment is occurring exactly at the center. So for which you divide the span exactly at the middle and name the axis as XX axis. Now, the UDL, half of the UDL you will get exactly at the center of the axis itself. Hence, up to center we need to consider the UDL part. That means we are already considering the half of the UDL here. So for remaining half, that is for half of the UDL, I need to the half of the UDL will be converted in terms of the point load now. So the half of the UDL means 20 multiply with the half of the distance. The total distance is 3.3. If you do half, if we consider the half portion, then you need to take 3.3 by 2. So 3.3 by 2 gives you a value of 1.65. Let us multiply 20 with 1.65. On multiplying 20 with 1.65, you get 33 kilonewton. Sorry, this is kilonewton. As you are converting UDL in terms of point load, you get a value in terms of kilonewton. So 33 kilonewton will be acting exactly at the center of the span of 1.65. That is at a distance of half of the span, which is of 0.825. Half of 1.65 gives you 0.825. So I have done this calculation, and I have drawn this figure just for making the calculation of bending moment easier. Now, let us find the reactions which are acting on the slab by considering the first part of the figure. Here, the first part of the figure has the UDL on three sides, that is on the midspan as well as first and the second portion of the slab. So we know that if we cut the beam if we cut the stair or the slab exactly at the middle, we can get the symmetry on the either side. Whatever the load that is acting on the left side of the axis, the same amount of load will be acting on the right side of the axis. For the symmetry, we will get the reactions both A will be equal to B. Now, the reaction A as well as B will be equal, and that will be equal to the total load which is acting on the slab divided by 2. Now, let us start with the first load. The first load is of 15.45 kilonewton per meter. As that is acting in throughout the span of 1.365, let us convert this in terms of concentrated load, that is 15.45 multiplied with its span length, that is 1.365. Then plus the second UDL is of 20 kilonewton per meter, and with that will be acting at a span of 3.3. Let us multiply 20 with 3.3. Then plus the third UDL is of 15.45, and that is acting again at a span of 1.365. Let us multiply 15.45 with 1.365. So that gives you the addition of the total load which is acting on the overall slab. So divide the whole thing with 2. And then you simplify it. On simplifying, you will get the reaction value of RA and RB as 54.09 kilonewton. Then, once the reaction is known to you, you start finding the bending moment, and we know that the maximum bending moment exactly occurs at the center of the span, that is at the axis XX. Then, to find the bending moment, as we have got the factored load here, I am directly writing the ultimate moment or MU value here. So MU is equal to, first, there is a reaction which is acting in the upward direction, and the action of the force with respect to the XX axis is in clockwise direction. If it is in clockwise direction, then we will be taking the force as positive value. So plus of RA into the distance from the RA with the XX axis is 3.015. Hence I have written this as 3.015. Then the second force which is acting on the slab towards left of the XX axis is of 21.09 kilonewton, and that is the concentrated load which is acting in the downward direction, and the point of application of this load towards the XX axis is in anti-clockwise direction. As it is moving in anti-clockwise direction, I am taking the negative sign here. Minus of 21.09 into, you have to take this, see the distance of point load with respect to the point, this point is of 0.6825. So the total distance that is travelled by the point load is 0.6825 plus 1.65. This gives you the total distance. Then the next point load is of 33 kilonewton, which is acting towards downward direction, and the point of application of that load with respect to the axis is again in the anti-clockwise direction. Hence I am taking the negative sign here. Minus of, the load is of 33 and it is acting at a distance of 0.825. Now you start simplifying, you first substitute the value of RA and then you start simplifying the whole equation. On simplifying the whole equation, you get a value of MU as 86.66 kilonewton meter. So that completes step number 5. Let us move to the next step. In step number 6, we have to check for the effective depth. Whatever the depth we got in the earlier step, whether the provided depth is correct or not. So for checking that, there is a formula to find the effective depth, that is square root of mu divided by 0.138 FCKBD. And this formula is only applicable if the grade of the steel is of 415. For 415 grade steel, the formula, we can apply this formula, where mu, just now we got the value of mu as 86.66, that will be in terms of kilonewton and meter. We need to convert kilonewton meter in terms of Newton mm by multiplying your value with 10 power 6. Then divide the whole thing with 0.138 and FCK is of 20, and we are assuming the width of the slab or the length of the slab as 1000 mm here. Then you simplify the whole thing. Let us start simplifying this. 86.66 into 10 raised to the power of 6 divided by 0.138 into 20 into 1000 is equal to, put square root for this. We get a value of 177.196, approximately 177.2 mm. Let us compare the depth with the depth provided in the earlier step. See, we have provided the effective depth of 250 mm. Let us compare 250 mm with the depth what we have got. See, the required depth of the slab is of about 177. But we have provided more than that. If the provided depth is more than the required, then whatever the design that we have done so far, that is safe. So that is how we will check the effective depth here. So that completes step number 6. Let us move to the next step. In step number 7, we need to design the main reinforcement. So for designing that, I am making use of IS 456-2000. From page number 96 of code book, you can get the formula mu is equal to 0.87 Fy ASTD into 1 minus AST Fy by FCKBD. The value of mu, we got it as 86.66. You multiply that with 10 power 6, hence for keeping mu in terms of Newton mm. Then put is equal to, then you write 0.87 into Fy value is 415. AST itself is unknown, you keep AST as it is, multiply that with the effective depth what we have provided, that is of 250 mm. Then open the bracket, 1 minus AST and Fy is 415, FCK is 20, and we are assuming the unit width here, hence the value of B is 1000 into again the effective depth is 250. Let us try to simplify the whole equation at a time. You put bracket 86.66 into 10 raised to power 6, close the bracket, alpha is equal to, again open the bracket, 0.87 into 415 into alpha A, then into 250, close the bracket, put multiplication sign in between, then open the bracket, 1 minus, open two brackets here, then again alpha A into 415, close one bracket, then divide, then open the bracket, 20 into 1000 into 250, close three brackets at the end. After that, you press shift calculate. If you are not getting in the single time, you will be getting twice. But if you press the button shift calculate, then shift calculated twice, then you will get the final answer of A. I got the final value of A as 759.59. Here the value A itself represents your AST value. So whatever the value that you get, that you have to write it down, that will be in terms of mm square. Now let us assume 12 mm dia bars are placed in the main reinforcement side. So now you have to find the AST of 1 bar. For finding the AST of 1 bar, we will need to multiply pi with the dia bar square divided by 4. We get a value of 113.097 mm square. Then let us find the spacing that is provided. To find the spacing, we have the formula small AST by capital AST into B, where the small AST value is 113.097 divided by capital AST is 759.59 and B is the unit width, that is of 1000 mm. On simplifying the whole thing, you get the value of 148.89, approximately reduce it to nearest value, that is 140 mm. Finally, you write a sentence as provide 12 mm dia bars at 140 mm center to center. So that gives you the design of the main reinforcement. Let us move to the next step. In step number 8, we need to design the distribution reinforcement. For designing the distribution reinforcement, we had to adopt the value of AST as the minimum AST, and the value is of 0.15 to 0.12% of gross area. Here I am adopting a value of 0.12% of the grass area. 12% means 0.12 divided by 100. That multiplied by gross area means B into D. That is the overall depth you had to take. Here you keep 0.12 by 100 as it is. B represents the unit width, that is of 1000, and capital D represents the overall depth. We got it as 280. Simplify the whole thing. On simplifying, we will get a value of AST as 336 mm square. Then let us assume the distribution bar of dia 8 mm, and now let us find the area of one bar. To find the area of one bar, we have the formula pi into 8 square by 4. That gives you 50.265 mm square. Then you find the spacing of the distribution bar. The spacing is small AST by capital AST into B. Small AST this time is 50.265, and capital AST, just now we got the capital AST value of distribution bar as 336 mm square. That value you need to take. That multiplied by B. B represents the unit width, which is of 1000 mm. Now simplifying the whole thing, we get 149.59. Reduce it to the nearest digit, that is 140 mm. And finally you mention a sentence as, therefore provide 8 mm dia bars at 140 mm center to center. So that completes the design part. At the end you have to sketch the reinforcement. So let us start sketching it. So first you need to show the clear span, the clear distance which is left out from the support and the staircase. Then the staircase starts. Here totally you have provided 12 number of rise and 11 number of threads. So you have to show 12 vertical lines and 11 horizontal lines. So that represents your step part. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have shown 12 number of vertical lines which represents the rise. And there is 11 number of horizontal lines which is provided in between the vertical lines. So that horizontal part represents the thread. So this is your thread, and then this is your rise. Then you start showing your main reinforcement. The lines, continuous line what I have shown within the figure represents the main reinforcement, and the circles in between or above the lines, horizontal lines represents the distribution reinforcement here. So here we have provided the distribution bars of 8 mm at a spacing of 140 mm. So for circles you have to show it as 8 mm bar at 140 mm center to center, and for the continuous line represents your main reinforcement, and we have provided 12 mm dia bars at a spacing of 140 mm. And this is the depth of the waist slab, that is the overall depth what we have provided, which is of 280 mm. So that gives you the sketch of reinforcement details, and that completes the design of dog-legged staircase. Thank you.